I wanted to make it a point to run through the 2006 AP Physics problem that I assigned for homework. So let's just begin. It says write a differential equation that can be solved to determine the charge on the capacitor as a function of time after S1 is closed. So we're going to go ahead and close this switch like that, leaving S2 open. So that means we have voltage that produces a current that goes out through here, goes around here, through R1, through the capacitor, and back into the battery. So we can write Kirchhoff's voltage rule for part A like this. We can say that the EMF minus I times R1 minus, now the voltage across the capacitor, again, let's remember that for a capacitor, Q equals CV. So that means here, the voltage across the capacitor is going to be Q over C. To convert, and this adds to 0. So to actually solve, we have EMF minus dQ dt R minus Q over C equals 0. All right. So it says write a differential equation. Now we're going to solve the differential equation in part A to determine the charge on the capacitor as a function of time, given EMF, C, and R1. I'm going to do this a little bit differently than we did the problems in class, where I'm actually going to use the variables. So if you look at the previous video where I solved the differential equation, here I'm going to do it with pure letters, keeping track of what's constant. So we're going to say, once again, we are in fact going to isolate some things. So we're going to say that dq dt times R equals EMF minus Q over C. Continuing, we're going to divide both sides by R, so we're going to say dq dt equals EMF over R minus Q over RC. And what I'm going to do here is basically multiply top and bottom of this fraction by C over C to give me a common denominator. So I'm going to get that dq dt equals CE minus Q over RC. Finally, we are ready for separation of variables. And in fact, what I'm going to do is I'm going to move part of this over here, just to give myself a little bit of room to work. And in fact, no, let's do it. Now I can solve using separation of variables. And that's going to look like this. So I'm going to basically say that dq over CE minus Q equals dt over RC. And now I'm going to integrate both sides. To do that, we will do a U substitution. So we're going to say that U equals C times the EMF minus Q, and negative du equals dq. Substituting that into the integral, we're going to end up getting negative du over u equals dt over RC, and we're going to multiply both sides by -1. So I'm going to get that the natural log of u plus our integration constant is going to equal t over RC. Let's go ahead and obtain that integration constant by noting that at t equals 0, q equals 0. So we're going to get the natural log, negative the natural log of CE equals our integration constant. Continuing, we're going to get that the natural log of C EMF minus Q over C times the EMF equals negative T over RC. As we continue on and on, we'll take e to the both sides, and I'm going to skip just a little bit of algebra here, just let you know that when we solve for q as a function of time, the answer for b is going to equal c times the EMF 1 minus e to the negative t over RC. And now I can put in my values. So Q of t, so 12 times 0.06, that's going to give me 0.72 times 1 minus e to the negative t over, and r times c is going to be 4,700 times 0.060. That's 282 right there. All right. And now it says determine the time at which the capacitor has 4 volts across it. So it actually turns out, since Q of t equals C times V, let's divide both sides by C. So I get a free formula here. It turns out the voltage across the capacitor is going to equal the EMF times 1 minus e to the negative t over RC, like that. So what we can do is we can plug in 4 and solve for the time, which we will not do right now. Now, for part D, we need to be really careful about what's going on. So let's write a couple facts down. So, at this new t equals 0, let's just be clear on a couple things. For part D, first, I1 is still going to be 0. And the other thing is, let's talk about t equals infinity. At t equals infinity, look at this circuit. The capacitor acts like a brake at time equals infinity. So the I through R1 and the I through R2 are the same. So I'll just draw a line down the middle. Okay? And what that tells me is that at time equals 0, let's just remember, at time equals 0, there was no current going through I1, and eventually we're going to reach some limit as time goes on. Now let's talk about the current going through R2 when we first start. When we first start, we're going to have a non-zero amount of current going through R2. Here's why. This current is 0, but we have this capacitor connected now to this resistor R2. So it's immediately going to start sending current through this resistor as though it were isolated just for that split second. So at t equals 0, I2 is going to be bigger than 0. And therefore, what we're going to see is, as time goes on, the capacitor will reach a new equilibrium with R2, R1, and the rest of the circuit. So we're going to have this very big I2 at first that is going to decay and match the I1 so that they are equal values like that. So that is part